Alright, Logic fans, welcome to our third video on 3.6. This is video 3.6c on conditional proof, and we're continuing along here. At the end of the last video, we talked about an application of conditional proof whereby you had a biconditional you were trying to show. And on that theme, there's another well-known sort of proof technique that uses conditional proof. It's called proof by transposition. You can Google it. Sometimes it's called proof by contraposition. We're calling it transposition. But the basic idea here is that you've already got a conditional. So first of all, you can solve this argument without conditional proof. But if you use conditional proof, you can assume A and look for B, and that's no problem, okay? But just by way of illustrating the method of proof by transposition, can you tell me, for example, what this conclusion looks like if I were to apply the rule trans to it? Okay, so if we were to apply trans, all right, then what we would have here is a situation like this. So the conclusion would really look like this. So we can imagine in our mind's eye the conclusion looking like this. And then what we can do is we can assume not B and look for not A. Now sometimes it's a lot easier to work with the transposed form of a conditional rather than the conditional itself. In this case, it's pretty easy either way. But it's a common technique because sometimes it's easier to assume this than it is to assume this. Okay, and you'll see that in practice on problems. But with that, go ahead and pause now. What would you assume and what would you look for? Okay, so hopefully you're getting the hang of it by now. The patterns should be emerging. In this case, you would assume not B, right? And that's an assump. And what you're looking for in this case is now not A. All right, so that's what we're going to assume. Now, what we're going to do is we're going to use our assumption of not B in conjunction with our premises to find not A. So pause now and find not A. Okay, this case isn't too bad, right? So not B combines here to get you D, and that's modus ponens on 1 and 3. And then, of course, we can do modus ponens again on 2 and 4 to yield the desired thing, not A. Simple enough, right? So modus ponens on 2 and 4 in that case. And now, having obtained what we wanted from our assumption, what do we do with our assumption? We discharge it, okay? Same thing every time, all right? And what do we write in line 6? You write the first thing you assumed, then you write down an arrow, then you write down the last thing you got there. All right? Okay, and then you're going to justify it how? All right, so we justify this by CP, and it's 3 through 5 in this case. Easy enough. All right, CP 3 through 5. Now, are we done? No. We asked for this, okay? So how do we get it? Well, what we're going to do is we're just going to use trans on that, right? So it's going to be pretty easy. All we're going to do is we're going to write this, and we're going to do trans on 6 to get that. All right, so that's all it is to it, okay? I mean, it's just there's all these different neat applications that you can use. And look, the big idea here is this. Really, you can kind of assume whatever you want, okay? You can assume whatever you want, and then you can discharge it whenever you want, but you got to discharge to a conditional where the antecedent is the thing you assumed, and the consequent is the last thing that you got, all right? And that's basically how it works. And after you really get it down, sometimes you can use some creative insight to see what you should assume and what you shouldn't. But my general advice for beginners is try to think of what the conclusion would look like as a conditional, and if it's or even as a transposed conditional, okay? And then that'll tell you that'll give you a lot of insight in how to solve the problem and how to proceed. So be sure you're checking out the examples in the book and working on those. Okay, one last application of conditional proof, and we will look at some advanced applications in 3.7. But here I want to observe and point out to you, and this is a really useful feature of conditional proof. We can use it to prove theorems. Okay, so here it says it's a theorem of logic that, if A and B, then A or B. And of course, that is a theorem of logic, and you proved it in section 3.5. What's interesting here is that we can use CP to prove theorems. So what we were doing before is we were using reverse engineering, right? And we were sort of trying to figure out, hey, can I manipulate this into something that resembles either the law of non-contradiction or the law of the excluded middle? And that's a perfectly fine way to go. And then because it's a proof, you don't have any premises, you're looking for an application of LEM or LNC. Well, the other thing you can do now is you can make an assumption, okay? And that's what we're going to do in this case. So for the sake of illustration, if you were to make an assumption in this case, it's already a conditional, what would your antecedent assumption be, and what would you be looking for? Pause now. Okay, so hopefully you got it, but what you're looking for, or sorry, what you can assume in this case is just the antecedent, right? It's the exact same process. I'm not changing anything on you. Okay, it's an assumption, and of course what you're looking for is the consequent here. All right, so now what you have to do is now you've got this thing on the board, your assumption, okay? And what you're doing is you're going to be manipulating this assumed thing, A and B, until you've got this thing. So working only with this, can you get this? Pause now. Okay, once again, there's not too much to, there's different ways of doing this, all right? So you're going to do simp, this is how I'm going to do it anyways, I'm going to do simp on 1, and then I'm just going to take the really, really easy route of just saying, okay, I'm just going to add B now. All right, so I'm going to just add on 2. And so now I've obtained what I was looking for here, okay? And so having obtained what I was looking for from this assumption, I'm going to discharge that assumption, and that's going to give me the thing I assumed, arrow, the last thing I got, okay? So it's the exact same procedure as we've been doing for all of these videos on 3.6. So the first thing I assumed was that. The last thing I got was that. Okay? And I'm going to justify that by CP on 1 through 3. And this is a proof, biconditional proof, of this string that it's a theorem of logic. Okay? This absolutely is a theorem of logic, and you can use it that way. Now, I invite you to compare this demonstration to the demonstrations offered in 3.5, where we reverse engineered this to LEM, okay? You'll find that this is a much cleaner one. It's a much more natural way to go. It says, if this is true, then this. Okay, well, assuming this, look at, you can get this. So, if this is true, then that's true, right? So it's a very natural way of arguing. Okay, logic fans, make sure you're trying all the practice problems, all right, so that you can really get this down. And conditional proof is really nice and historically well-trodden sort of problem-solving technique. Get lots of practice with it, because we're going to use it in 3.7, and then we're going to see what's basically a variation on it in 3.8 and 3.9. So it's important to get down well now. Catch you on the next videos.